Welcome back, and today we'll see a topic which is a continuation of Fourier series. And we know what was Fourier series. We have seen two types of Fourier series expressions or expansions. One was using trigonometric functions, and where we evaluated a naught, an, and bn. And in some cases, we could find some symmetry conditions where we only found a naught or an, and in some cases we found only bn. Okay, and then in the second form of Fourier series, which was more or less a very compact form of Fourier series, and that was actually the exponential Fourier series. And we have seen 2-3 examples also regarding that. And there the advantage was we have to evaluate only one parameter, that is Cn bar. Okay, so Cn bar, if you find Cn bar, we can easily plot the magnitude spectrum as well as the the phase spectrum. Okay, and you may wonder what is the advantage or what is the use for that magnitude spectrum and phase spectrum. The reason is that you have a periodic signal, a non-sinusoidal periodic signal, okay, and you're trying to write it as an algebraic sum of so many sinusoids starting from zero frequency, fundamental frequency, then the harmonics, that is the multiples of the fundamental frequency. See, the whole signal or the signal can will lie, the magnitude will lie at several frequencies. Okay, this much magnitude of that signal will lie in sometimes the DC, or sometimes the fundamental, sometimes third harmonics, sometimes the fourth harmonics. Okay, and you might have drawn some diagrams in the last, I have shown that in the last video, where that is this much magnitude of that signal is present in such a frequency. So how much magnitude of that signal is present in what frequencies we can actually find using that magnitude for spectra. Likewise, phase, what is the phase in this at this frequency. Okay, so that's a collection, so you will get an idea of what is a magnitude, how much strength lies in such a frequency, or what is a phase in such a frequency. Okay, you are actually splitting or you are analyzing a signal which is periodic but non-sinusoidal by converting that into so many forms of sinusoids. Okay, so that is the advantage of Fourier series. So, okay, now we start from that exponential expression, that is exponential Fourier series. You know that what is Cn bar, and that is given in the box here, that is Cn bar is equal to 1 by t naught integration from minus t naught by 2 to t naught by 2 f of t e raised to minus j and omega naught t dt. Okay, now suppose if you have a periodic signal, we start from a periodic signal, and Fourier series were of course described for Fourier series. And suppose we start from a pulsating waveform as shown above, that is with a period of t naught. A pulse has a duration of small d and a height of capital A. And suppose if you write the Fourier series for that, exponential Fourier series for that, and draw the spectrum. Okay, it's not magnitude or space, simply spectrum. That is, you are plotting Cn bar against n omega naught. You are plotting Cn bar against n omega naught. You can plot magnitude of Cn bar versus n omega naught or n. Or you can plot the phase of Cn bar against n omega naught or n. Okay, whichever is possible. Okay, you can draw, that is magnitude and phase. But right now I am drawing only magnitude and phase spectrum in combination, that is simply Cn bar against n omega naught. And you'll get a diagram which is shown in the top left of that screen. That is, you have so many spikes. The red lines over that is the envelope. Okay, it's not the actual continuous line there. It is actually, I'm just joining the top points of that spectral lines, and I'll get an envelope of that diagram. That is what. Okay, so if the signal is continuous, though the signal is continuous, the spectrum you get is discontinuous. That is the inference. Okay, even though the signal is continuous, the spectrum you are getting is actually discontinuous. Okay, and for that the Cn bar mathematical expression is shown there. That is a into d divided by t naught sine n omega naught d by 2 by n omega naught d by 2. That is equation number 1 shown there. That is actually the Cn bar. You may try at home to get that Cn bar. Okay, where Cn bar we have already discussed, it is nothing but Fourier coefficient, and Fourier series, in exponential form can be written as f of t equal to summation from n equal to minus infinity to infinity Cn bar e raised to j n omega naught. That is a compact form of exponential Fourier series. Okay, now suppose for that waveform I have shown above, if I suppose t naught to be very large. Okay, so we have seen the equation, just see the equation number 1, just see the figure above that equation number 1, and suppose if I make the time period very large, like I have shown below at the center page, that is t naught is very large. So what happens when the time period is very large? And for that time period of very large, I mention that t naught L, that is just to mark that the time period is very large. Okay, so what happens is that you can see the diagram there. So what happens to that Cn bar when t naught is very large, the denominator is very large, a you are not going to change, or d is not going to be changing, and the t naught is very large, so denominator becomes very large. So what happens? The magnitude of Cn bar reduces, or the plot that you have seen at the top right of the screen crashes. Okay, and you can see that in the middle page you can see this now the spectrum. What is the shape of the spectrum? Even though the lines are there, the height of that lines are very small, because t naught L is very large, time period is very large, all the whole spectrum crashes almost to the horizontal line. Okay, and there is no meaning in observing such a spectral line with very feeble magnitude. Okay, and there is no point in continuing with such an analysis. Okay, so we make a small adjustment there, we make a small compromise to regain the magnitude. So what we try to do is that we have Cn bar, to that we multiply t naught of L. Already we have Cn bar, if we multiply that t naught of L, so what happens? That t naught at the denominator of Cn and TL that gets cancelled, because now the time period t naught is t naught of L. So that t naught of L, if you multiply with Cn bar, the denominator time period and this time period get cancelled. And what you that t naught was the biggest problem, which reduced the magnitude of the spectrum. So we are avoiding that defect there by multiplying Cn bar with Tn naught L. So what is happening is that, so what happens when Cn is multiplied with T naught of L? That is T naught of L is time period. Time period is nothing but 1 by frequency. You can write it as Cn bar divided by delta f naught. Why I am writing delta f naught? If time period is very large, then the frequency is very small. That very small frequency I am writing it as delta of f naught. Initially the time period was T naught, then the frequency was f naught. Now the time period is very large, so the frequency will be very small. So fractional frequency I am representing it as delta f naught. Okay, so Cn bar divided by delta f naught, and that is equal to Cn bar by delta f naught can be written as delta omega naught by 2 pi. Okay, so that Cn bar divided by delta omega naught by 2 pi is written as Fourier coefficient density. That is a very important point. Just listen. That is Cn bar divided by delta f naught can be written as Cn bar divided by delta omega naught divided by 2 pi. And that thing, that is Cn bar divided by delta omega naught by 2 pi, is known as Fourier density coefficient. Fourier coefficient density. Okay. Now just see the plot at the bottom of that page 1. That is, now it has regained the original shape, original magnitude. That is because AD, initially the height was AD by T naught. Since we considered a very time period, the whole thing's crashed to the horizontal line. Now that T naught is cancelled because we multiplied Cn bar with T naught of that T naught L, and T naught gets cancelled, and you got the original height. That is, now the height is a into d. Denominator has disappeared. Initially denominator, initially it was ad by t naught. Now t naught has cancelled. Now there is one thing you have to note, and okay, the x-axis was n omega naught. Now it has become n delta omega naught. You might have understood that thing. That is, omega was the initial frequency. Now the time period, as it was very large, now it is actually n delta omega naught. Okay. Now, what is the first zero crossing frequency there? What is a zero crossing point there? And we just see the equation number 1. That is, the whole thing becomes 0 when it is the angle is angle is pi. Okay, that is the first zero crossing point. And we are actually drawing we have drawn the spectrum with x-axis n omega naught. So if we substitute something for n omega naught, that is, the whole angle will be pi. And what is that angle? What we should substitute for n omega naught, so that n omega naught d by 2 becomes pi? The answer is, you can substitute, it is shown there. You can substitute, instead of n omega naught, pi by d by 2. If you substitute instead of n omega naught as pi by d by 2, then d by 2 and d by 2 gets cancelled, and then 2 and 2 gets cancelled. That angle becomes pi. So sine pi is 180, sine 180 is 0. So everything becomes 0. So that is the first point. Okay, that is, you can see that pi by d by 2 is nothing but 2 pi by d. So the 2 pi by d is the first zero crossing point in that spectrum. Okay, now recall, that is, f of t is equal to summation from n is equal to minus infinity to infinity cn bar e raised to jn omega naught t. Now we substituted instead of cn bar. Okay, in that equation we can substitute instead of cn bar, that is, we substitute cn bar multiplied by t naught of L, and that is equal to, we know that is cn, that is equal to cn bar divided by delta omega naught divided by 2 pi. And we have described that with a name, that is called Fourier coefficient density. Cn bar divided by delta omega naught by 2 pi is called the Fourier density, Fourier coefficient density. Okay, and that should not affect the value of f of t. So f of t should remain the same. Whatever we had in the box should be the same. So if you multiply with t naught of L with cn bar, then correspondingly that should be adjusted. Okay, so how can that be adjusted? So when you substitute instead of cn bar with cn bar by delta omega naught by 2 pi, we have to multiply it with delta of omega naught, that is there, and then 1 by 2 pi, that is 2 pi. So that 2 pi should be adjusted by multiplying by 1 by 2 pi. That is why 1 by 2 pi is coming outside, and delta omega naught is being multiplied inside the summation. Inside the summation. Okay, so everything, all other things will remain the same. I hope you have understood. We have multiplied with 1 by 2 pi and delta omega naught to compensate for what we are having under cn bar, that is delta omega naught by 2 pi, and that is given as equation number 2. Okay, now we are moving on to the actual thing. Okay, so till now we have seen we have started from a problem and reached this point. Okay, till now we started from a time period t naught, which was a normal time period, and it had a normal frequency, and then we moved on to a large time period, that is t naught of L, so that the frequency reduced from f naught to delta f naught, or frequency reduced from omega naught to delta omega naught. Okay, now we are considering a thing called a periodic function. What is a periodic function? And I already told that Fourier series was discussed for was defined for only periodic signals. So a periodic signals, there were so many periodic signals. They were very sad that they were not considered by Fourier in their analysis. So you can consider a periodic function as a periodic function with a time period infinity. That is the crux of that the analysis. That is, any aperiodic function is periodic with a time period infinity. You can consider that. And such a diagram is shown in there. That is, there is only one pulse for an aperiodic function. There is only one pulse. I'm taking over from the example stated above. I've taken the same example above. That is, you have considered a pulsating waveform there, and if that pulsating waveform is having infinite frequency, infinite time period, then you can actually see only one pulse of height a and width d in the entire time period. That is the meaning of period infinity. Okay, so if time period tends to infinity, then what happens to frequency? However small, that tends to 0. If time period tends to infinity, then my frequency delta omega naught also tends to 0. So that is thing. So what is the thing happening with the spectral lines? So when, see, we have plotted, see the x-axis of that, the diagram shown there. See, when time period tends to infinity, then delta omega naught becomes very small. So if delta omega naught becomes very small, what happens to the spacing between the lines? The spacing between the lines becomes so close. Spacing between the lines becomes so close. So when it becomes infinity, what happens? When it becomes infinity, the lines become so close that at every point on the x-axis you have a spectral line. I repeat, when time period becomes infinity, the frequency becomes almost 0 or 0, so that on the x-axis, on every point on the x-axis you have spectral lines. So what is the meaning of that? You get a continuous waveform. That is, your waveform or the spectrum becomes a continuous one. Okay, or the n delta omega naught can be replaced by a continuous running variable omega. That is, since the spacings cannot be distinguished, or since the spacing between the lines are negligibly small or negligible, or since every point on the x-axis has spectral lines, you can replace. That is continuously. That is the meaning of continuous. Okay, you can replace n delta omega naught by a continuous running variable, that is simply omega. Okay, so even though your signal was continuous, even though your spectrum was discontinuous, now for an aperiodic function you can see that the spectrum becomes continuous. So for an aperiodic function, your spectrum becomes a continuous one. Okay, now the Fourier coefficient density, which I have described in detail earlier, that is Cn bar by delta omega naught by 2 pi. That was a Fourier coefficient density that I can replace by a term called f of j omega. That Fourier coefficient density, which I have explained earlier, can be described by a simple function, that is f of j omega. That is Fourier coefficient as a function of frequency, f of j omega. And you can actually go back a little bit. Okay, that is what was f of c. Okay, that is Cn bar. See the equation inside the box. Cn bar, that was the point where we started. Cn bar, if you divide by if you multiply it by T naught of L, that is actually the Fourier coefficient density. So if I multiply by T naught of L, okay, or a very large time period, okay, then what happens? Then 1 by T naught disappears, because you are multiplying the whole thing by the time period, so the time period disappears. And that is why for this Fourier coefficient density f of j omega, you don't have 1 by T naught outside the integral. So that point is clear. Okay, so and then coming back, then we are considering time period infinity. So the limits of integration will be from minus infinity to infinity. You can see that here the limit of integration is from minus infinity to infinity. We are applying all the case here. Okay, that is when it is an aperiodic case. Okay, now so far we have discussed the background. Now we are applying the limiting condition, that is the infinite period and zero frequency, into the two equations. Okay, that we have stated earlier. Okay, and then we have f of t. F of t will remain the same. Then we have e raised to minus jn omega naught t dt. Now that became n delta omega naught because the frequency was very small, and since the period tends to infinity, delta n delta omega naught also tends to 0, and you can replace n delta naught by a continuous running variable omega, or you can see that that can be written as f of t into e raised to minus j omega t dt. So n delta omega naught is replaced by a continuous running variable omega. Okay, and that equation number 3 is called the Fourier transform of f of t, and that equation shown in the box, equation number 3 shown in the box, is the Fourier transform of f of t. Okay, now applying the same limiting case. What was the limiting case? Time period infinity, frequency 0. In equation number 2, what is equation number 2? Equation number 2 is this one, that is f of t is equal to 1 by 2 pi summation from n is equal to minus infinity to infinity cn bar by delta omega naught by 2 pi into e raised to jn delta omega naught t delta omega naught. That was equation number 2. So when we apply, what happens? I already said that cn bar by delta omega naught by 2 pi, which is the Fourier coefficient density, is written or represented as f of j omega. So f of j omega. Now what happens to the summation? I told that at every point on the x-axis you have the spectral lines. That means at every point on the x-axis, if you have spectral lines, then that means it is continuous horizontal line. It's a complete horizontal line. That means that is continuous summation. So that continuous summation, it can be replaced by an integration. Continuous summation is nothing but integration. Okay, so that integration will be from minus infinity to infinity, and outside you have 1 by 2 pi, and that is written here. So f of t, which is replaced, which is f of t, which is shown in equation number 2, can be written as f of t is equal to 1 by 2 pi will remain the same. Continuous summation can be replaced by an integration from minus infinity to plus infinity. The whole thing, that is Fourier coefficient density, can be represented as f of j omega. Then e raised to minus jn delta omega naught. N delta omega naught can be replaced by a continuous running variable omega. So that becomes e raised to j omega t. Then delta omega naught becomes d omega. Okay, and this is called the Fourier integral or the inverse Fourier transform. Okay, so these are the two equations required in Fourier transform. One is the Fourier transform of f of t, and then the other is the Fourier integral. Okay, and remember, Fourier transform and Fourier integral are defined for aperiodic signals, and Fourier series was defined for periodic functions, and this is defined for aperiodic functions or signals. Okay, so these are the two equations you have to remember, and we'll see some examples, few typical examples in the next class or the next video. Thank you.